So let's do some ideal gas law calculation practice. Just so that we have it handy, I'm going to write the ideal gas law up here, PV equals nRT. And just as a reminder, in general, we're going to be looking for the pressure to be measured in atmospheres, the volume to be measured in liters, N is the number of moles, R is the ideal gas law constant, and T is going to be measured, temperature is going to be measured in Kelvin. So our first example here, at what pressure, so we know we're going to be solving for pressure, would 0.15 moles of nitrogen gas at 23 degrees Celsius occupy 8.90 liters. You may recall that we can use the ideal gas law, its basic form, without knowing what type of gas we have. And so as a result, I kind of skipped right over the fact that this is nitrogen gas because we don't actually really care to be able to solve this problem. So what we know is we need to solve for pressure. So I'm going to rearrange the ideal gas law. P equals nRT over V. And I'm going to start plugging in my values. 0.150 moles times the ideal gas law constant, 0.0821 liter atmosphere per mole Kelvin, times the temperature. Now the temperature is 23 degrees Celsius. And so I'm just going to take a little detour over here, and I'm going to say 23.00 degrees Celsius plus 273.15 is equal to our temperature in Kelvin, which is 296.15 Kelvin. So now I can put that temperature in here, 296.15 Kelvin, and all of that is going to be divided by my volume, which is 8.90 liters. Now let's take just a second and look at the units. Notice that my moles here will cancel with my moles here. My Kelvin here cancels with my Kelvin here. And my liters here calculators with my liters here. So I'm left with atmospheres, which is good because I'm looking for pressure. So I should end up with units of pressure. And so if I plug these numbers into my calculator, what I get is 0.4097 atmospheres. And I should only have 3 sig figs, so I'm going to round that to 0.410 atmospheres. Okay, let's look at our second problem here. A gas occupies 12.3 liters, so we know its volume, at a pressure of 40 millimeters of mercury, so we know it's something about its pressure. What is the volume, so we must be solving for volume, when the pressure is increased to 60 millimeters of mercury. Now this is a slightly different type of problem in that we know volume, we know pressure, but we haven't been given a number of moles and we haven't been given a temperature. So in this case, what we have to recognize is that we can use the ideal gas law in the following way. We can note that N must be constant in this problem because we're just taking the same sample and increasing the pressure. So N is constant, T is constant, and of course the ideal gas law is constant. And since I'm just going to rearrange the ideal gas law here and write nRT over here, that's equal to pressure times volume. And since nRT is constant, the first pressure and the first volume must be equal to the second pressure times the second volume, because each time this pressure has to be equal, this pressure and volume multiplied together have to be equal to nRT, and this pressure and volume multiplied together has to be equal to nRT. So now we don't need to worry about what NR and T are. We can just focus on this part of the equation. Now, I'm going to go ahead and I'm going to convert my pressures 2 atmospheres. It's not always strictly necessary in every single problem, but I think it's a good habit to get into. So I'm going to say that pressure 1 is equal to 40 millimeters of mercury. And to convert that to atmospheres, I'm going to say there's 1 atmosphere per 760 millimeters of mercury. And that gives my first pressure to be 0.05263 atmospheres. And I can see I'm not really going to have enough room here, so let me see if I can fit my pressure 2 up here. Pressure 2 is equal to 60 millimeters of mercury. Again, 1 atmosphere divided by 760 millimeters of mercury is equal to 0.07894 atmospheres. Okay, so now recognize that I know the starting volume and the starting pressure, that's P1 and V1, and I'm looking for the volume. I'm looking for V2, and I have pressure 2. So let's see how this rolls out. So P1 is equal to 0.05263 atmospheres times the starting volume, which is 12.3 liters. And that has to be equal to the ending pressure, 0.07894 atmospheres, times V2. So if I now solve for V2, what I get is 8.20 liters. Now let's double check our units here. The atmospheres are going to cancel out with one another, and it's going to leave me just with liters in my answer, which is what I want. Let's make sure that this makes sense to us. What we've seen is that the pressure went from 40 millimeters of mercury to 60. We've increased the pressure. And what we determined is that in class if we increase the pressure, volume should decrease. And so we've got 12.3 liters to start with, and it decreases down to 8.2 liters. So that answer makes sense. This next problem is somewhat similar to the last one in that some things are constant. So let's read the question first. A gas occupies 1 liter at standard temperature. Assuming no change in pressure, what is the volume if the temperature is increased to 333 degrees Celsius? So let's see what we know. What we know is that standard temperature, let me just do this in black, I don't know why I care, but standard temperature is 273.15 Kelvin. In this case, what is constant? The number of moles is constant, R is constant, and P is constant. So we're assuming no change in pressure from the start of our problem to the end of our problem. So what we're going to do is we're going to take the ideal gas law and rearrange it so that these things that are constant are on one side and everything else is on the other side. So the way that looks is, let me just actually start it from scratch. PV equals nRT. So I'm going to put the N, the R, and the P together. So what that's going to look like is nR over P is equal to V over T. And as we saw in the last problem, since these are all constant, that means that the first volume divided by the first temperature, which we are now going to call V1 T1, has to now equal V2 over T2, because in both cases, both the starting conditions and the end conditions, the N, R, and the P will be constant. So if we now try to solve this, we know that the starting volume is 1 liter, and the starting temperature was 273.15 Kelvin. We do not know the ending volume, that's what we're looking for, but we do know the ending temperature, which in this case was 333 degrees Kelvin, and so I'm going to say T2 is equal to, sorry, I said that wrong, 333 degrees Celsius plus 273.15 Kelvin. This is a very high temperature. I'm not really sure why this problem has it so high, but it is what it is. So that is going to be 606.15 Kelvin. If we now solve for V2, what we get is 2.219 liters. And if we round to the correct number of sig figs, we get 2.2 liters. Now let's ask ourselves if this makes sense. What we learned in class is that we've got a temperature here and a particular volume. If we increase the temperature, we would expect the volume to increase, and that is in fact what has happened. So we're good. This next one, which somehow got out of order on this sheet relative to where it is on your sheet, asks how many moles of gas are contained in 890 milliliters, so we know the volume, 21 degrees Celsius, so we know the temperature, and 750 millimeters of mercury of pressure. So this is a fairly standard ideal gas law problem. We can rearrange the ideal gas law to be PV, N equals PV over RT. And let's just make sure that all of our values are ready to be plugged in. Let's convert the pressure from 750 millimeters of mercury. And we know that there's 1 atmosphere per 760 millimeters of mercury. And so we get, for that pressure, what do we get? We get, I don't know what we get. We get 0.98684 atmospheres. And that's going to be 4 sig figs. And we also need to convert our temperature. Our temperature is going to be 21.0 degrees Celsius plus 273.15, and that gives us 294.15 Kelvin. So now we just have to plug our numbers in. Our pressure is 0.98684 atmospheres. Our volume is 890 milliliters. I'm going to convert that on the fly to 0.8900 liters. Our ideal gas law constant is 0.0821 liter atmospheres per mole Kelvin. And our temperature is 294.15 Kelvin. And that comes out to be, what does it come out to be? 0.364 moles. Notice that in this particular problem, we don't even know what kind of gas it is. It's just moles of gas, because we can use this, the ideal gas law, in this way when we're relating PV, RT, and N without we can do that without knowing what kind of gas we have. Let me just go back and double check units here. Notice that atmospheres cancel with atmospheres here. Liters cancel with liters here. Kelvin cancels with Kelvin here. And notice that this moles that we have left is in the denominator of the denominator. And that brings it up to the numerator so that we have moles in our numerator, which is what we want in our answer. Okay, one more problem here. 96.0 grams of a gas occupies 48.0 liters, so we have a volume, at 700 millimeters of mercury and 20 degrees Celsius. What is its molecular weight? So this is a little bit of a different problem. Remember that molecular weight is measured in grams per mole. It's the number of grams that you would have if you had a mole of a sample. Now, we have a tendency to look at this 96 grams and think, oh, I've got to convert it to moles or something. The problem is we don't know what kind of gas it is. If we knew what kind of gas it was, then we would actually be able to just look up its molecular weight on the periodic table. So in this case, what we're looking for is we've got the mass of our sample. If we could figure out how many moles were in that sample, we could take the ratio between mass and moles to get the molecular weight. And we really do have enough information to do that, because we've got volume, pressure, and temperature, so we can solve for how many moles are in this sample. I'm going to go ahead and do the conversions that I need to do first. So I'm going to say the pressure is 700 millimeters of mercury, and I know that in 1 atmosphere there are 760 millimeters of mercury. So that gives me 0.92105. Oh, and this was 700.0, so let's keep 4 sig figs. Atmospheres. That's our pressure. I know that my temperature is 20 degrees Celsius. If I'm going to convert that to Kelvin, I'm going to say 273.15 Kelvin. So that's 293.15 Kelvin. So now I can use the ideal gas law. N equals PV over RT. So I get my 0.92105 moles. My volume, which is 48.0 liters. My gas constant, 0.0821 liters atmospheres per mole Kelvin. And my temperature, which is 293.15 K. And that gives me 1.8369 moles of gas. But remember that what I'm looking for here is I'm looking for the molecular weight. I want to know if I have a certain number of grams, how many moles do I have? So I can take that ratio. Well, I have the grams, and I now know how many moles are in that sample. So now what I can do is say the molecular weight, or the molar mass, equals the 96.0 grams divided by 1.8369 moles. Now, let's stop and talk about this for just a minute. What this tells us is that we have a sample that has has a mass of 96 grams, and in that sample there are 1.836 moles. We want to know what is the mass if we have 1 mole. So we're just going to divide through, and what we get is 52.261 grams per mole. Rounded the right number of sig figs, we get 52.3 grams per mole. So for this sample, when we had 96 grams, we had 1.8 approximately moles. But if we only had 1 mole, we would have 52.3 grams.